Hello, everyone. Greetings from Moscow, Russia AI meetups. My name is Dmitry Filatov. I'm an ambassador for Pie&AI meetups hosted in collaboration with Deep Learning AI. This is our second Pie&AI meetup here in Moscow, Russia, and tonight we will hear from Dmitry Nekhaev, who is a senior researcher at tech startup VisionLabs, a captivating story of winning face recognition vendor testing program organized by American National Institute of Standards and Technology. The second part of Dmitry's talk will be about recent advances in computer vision and face recognition algorithms and techniques. Dmitry graduated from Moscow Institute of Physics and Technology and completed his postgraduate studies at the Kurchatov Institute in Moscow. And both organizations are much respected research bodies across the world. Dmitry joined VisionLabs 3 years ago in 2017. And I am thrilled that today we have a chance to learn from Dmitry, who is at the forefront of applying advanced deep learning techniques to real-life computer vision problems. And I should stress that VisionLabs algorithms, not only academia, they are in production, and names of VisionLabs customers speaks for themselves. Hello, Dmitry, and thank you very much for joining us today.
Hello, Dmitry. Nice to meet you. Hello, everyone. Thanks for joining us.
Well, we really appreciate that all of you are taking some time for this event today. And before starting the presentation, I would like to say a couple of words about Pie&AI meetups and touch some housekeeping issues. Pie&AI meetups is an initiative launched by the Deep Learning AI. These meetups help people across the globe to communicate, explore, and share ideas within the broad field of the artificial intelligence. The purpose of Moscow, Russia AI meetups is to integrate Moscow into the worldwide deep learning community and to provide space for experience sharing and exchange of opinions on AI topics, both on local and on international scale. Before I finally pass the word to Dmitry, just a couple of housekeeping issues. First of all, this event is being recorded, and there will be a link to the YouTube channel. I will share this link a bit later in the chat and then in the event, in the email. We will also share a version of presentation and a reference list with resources. Post-event survey, please leave feedback after the event. The link for the survey will be provided by the Deep Learning via email. Those who will complete the post-event survey will get a limited course promo for 50% discount for first month subscription to any of Deep Learning AI's courses on Coursera online platform. Questions and the Q&A session, please use the chat to ask your questions either in English or in Russian, and we will do our best to answer as many as possible at the Q&A session after Dmitry's talk. Finally, if you have any unanswered questions or inquiries, please feel free to email me at info@atokerino.com. I will share this email also in the chat later. And now I will pass you over to Dmitry Nekhaev. Dmitry, the floor is yours.
So now I will share my screen. Can you see it? Okay, so let's start. Thank you for the invitation and for the introduction. Today's title of my talk is Winning NIST Facial Recognition Test and How We Did It. And here is a short plan of my talk for today. It is divided into 3 main sections. The first one, in the first section, I will give a small introduction about VisionLabs company. In the second section, I will talk about the NIST face recognition test. We'll give a general overview, and we'll talk about main challenges of this test. And in the third section, I will be about trends and technologies for face recognition and computer vision. So let's start with the company overview. I will give some face recognition use cases and project examples that we have. So what is VisionLabs today? We are top 3 in face recognition for at least last 2 years. So currently we are on the 2nd place. Also, we have top ranked technologies for emotion recognition and liveness detection. I will talk about it later. Our technology is used worldwide. So more than 1,050,500,000 cameras are connected to our system. And also we are fully GDPR compatible, which means that we are compatible with laws of most of the countries. Other face recognition companies do not do this in such level. We have a headquarter office in Amsterdam, R&D centers in Amsterdam and Moscow, and also we have offices in Singapore. And this year, we opened offices in USA and Dubai, and also plan to continue expansion in Asia with offices in Taipei and Tokyo. And let's talk about how our products work. We have our own core, our own framework for neural network inference. It is optimized for different kinds of running devices, different servers, mobile phones, GPUs, NPUs, processors, and so on. And it works faster than analogs. The next level is software level, with possibility of usage of our products for other third-party developers for their own solutions. And also we have our own products. The first one is Digital ID. It is a platform that allows to convert organization processes into digital, so the clients can be served remotely with highest level of informational security. For example, it can be used for banks, insurance companies, and so on. We have Luna VMS product. This is a product for video analytics, and also we have product Luna Auto, system for traffic monitoring for safe cities. And finally, we have our proprietary and co-branded smart devices. Some of them I will mention later.
Dmitry, just can I ask a question?
Oh yeah, of course.
VisionLabs was a tech startup, one of the many. What were the key elements of becoming such a recognizable company operating now in several countries and having big names among customers?
Okay, so VisionLabs products and solutions are based on proprietary algorithms. One of our main competitive advantages is the accuracy of face recognition. This is confirmed by the leading positions in international competitions and independent testing such as NIST, as I will mention it later. And another important advantage of VisionLabs is that we have 2 times lower cost of ownership or usage of the product as a whole than our main competitors. Our products do not require expensive additional hardware resources on the customer side due to high optimization of the neural network architecture and efficient storage of biometric templates, the descriptors. And I will tell about this in details a bit later. This is especially important when working with large databases and is relevant for banks, transport, and industrial infrastructure. Maybe something in some other objects.
Yeah, that's quite impressive. And one more question here, please.
Okay.
VisionLabs not only develops algorithms and works on deployment of application and platforms at customer side. The company also sells proprietary devices, and we will see this later, and even a range of these devices. So why the company decided to go into the material world in addition to development of programs and applications? And my second question here is, what is the proportion of employees involved in research and development compared to those in engineering and those in production?
Okay, so the devices are a unique offer because we can develop both algorithms and hardware by ourselves. In addition, we protect all this in terms of cybersecurity. Since everything is created within the same company, the hardware and software perfectly match to each other. We made many attempts to work on other clients' devices, but in the case we couldn't control everything. And when you fully control the process, you can act with all the responsibility for the customer. So we often see that our market colleagues have poor results and they blame clients' cameras, and we don't want to be in this position. So talking about the proportion, actually, I cannot tell you the exact proportion, but I can tell you that we divide research and R&D center in research and development. So we have divided team of researchers, and we have divided team of developers. So researchers do the research on face recognition algorithms, face detection algorithms, and so on. And developers are focused on making this algorithms work in product.
Okay, thank you. Thank you.
Okay, I can continue. Okay, so let's start with some face recognition use cases. In this talk, I will focus only on those technologies and use cases that are based on face recognition algorithms, and here you can see the list of them. I will shortly talk about them. One of use cases for face recognition is credit fraud prevention. This is an actual problem in banks, and one of the first cases of implementing VisionLabs technologies in production. So the situation is as follows. People come with fake passports to take a loan and do not return it. Banks and credit bureaus have large database of borrowers, including scans of their passports. We can keep a blacklist of such unfair borrowers and recognize them by their face. And the face is much more difficult to fake than the passport. And if we recognize them on the blacklist, we do not give a loan to such bad guys. Okay, the next use case is know your customer. It's quite interesting. Literally, we want to recognize our clients by their face without presenting a loyalty card or a passport. Typical cases are replacing the loyalty card with a face at the bank entrance or any shop when you buy something, and displaying all the necessary information about the client to the operator before they present their passport. Also, it can be used for recognizing some VIP clients, passing to VIP lounge of the airport, and so on. And another case is customer flow analysis, and this is closely related to the previous one. We can count how many people visit our client, which of them are unique, which of them visit store regularly, and what is their age and gender. So what can these attributes be used for? For example, if your shop or store has a video surveillance camera installed, in addition to using it for security purposes, you can also analyze the flow of visitors and get the load of your store at different times of the day and week. Based on this information, you can prevent creating of queues inside the store, like on these red areas to the left. Or you can see what periods of the day different age groups of people visit you. We had a case with one Japan company that has more than 100 shops in Tokyo with different locations. So before they used our solution, they had the same product line everywhere. And then such a system was installed, and they found out that shops have different distribution of visitors. So they optimized their product lines in these stores based on such a gender pyramids, and increased revenue and every check in the shops. And the classic application for recognition technology is access control. In this case, we replace the badge part with a face, making it impossible for a person to forget their work passing card. It also becomes much more difficult to fool the system by transferring the pass card to third parties. So in this direction, we develop not only software, but also hardware. In other words, we produce our own hardware complexes or devices with the face recognition function, which can be connected to a large system of turnstiles. There are devices in small and
turnkey solution.
What?
A turnkey solution.
Yes,
so
yes, yes.
A client and can provide everything and install with yourself. I mean, your employees or employees from your partners.
Yes, I will. There will be a demo in a few slides later to show you how it works. So there are devices of different range, form factor for installation on the doors or somewhere else. And also we made a version of the device with a thermal camera. So in addition to face recognition, it allows you to measure the temperature of the human body. So this is a video for our device. So it can store up to 500,000 face descriptors on this device. It is completely developed by VisionLabs, both hardware and software. It has RGB and infrared cameras for face recognition and liveness detection, and it contains NFC model, and it is compatible with cars too. Also, you can add a PIN code access on this device, so it supports 3-factor identification. And here are the examples of how it works. This is a demo of how it works when installed on doors, on the entrance, in metro station, and in the office. So you can see that people pass without making any noise. So another application of facial recognition technology that is quite interesting is paying with a face, or we call it selfie to pay. In this case, we also develop a terminal that allows you to pay for your purchases without taking out your card. And this is a short video of how it works. You can see here a man that is purchasing the bottle of water. He chooses to pay with the face, looks into the camera, and that's all. It is very fast. And the last use case that I will talk about is digital ID. As already mentioned, with digital ID, clients of any bank or insurance company can be served remotely with the highest level of informational security. And this is a demo example of how it works in application of bank in United Arab Emirates. This is one of the biggest banks there. So a person here scans his documents. All the data is recognized, so the person shouldn't do anything additional. So we recognize this data. We scan 2 documents for Arab Emirates, and if system verifies the data and if data is correct, the person becomes a client of a new bank. Now I'll tell some project examples that we have. The first one is Safe City Singapore. If you will be someday in Singapore, look to the camera and smile. All cameras work on our platform. There are more than 50 million faces in the database. So we work in Airport Charles de Gaulle. Air France employees go to the work with usage of our face recognition system, and also NVIDIA uses our face recognition platform for access at headquarter office. Another example is Royal Caribbean Cruises. It is one of the biggest cruise companies in the world. It uses our face recognition on self-check-in terminals for passengers boarding. Also, Police in Dubai and Abu Dhabi uses our mobile face recognition with more than 1 million faces in the database. And also many Olympic objects in Japan also operate with our access control system. This is how employees of some construction or building projects and stadiums go to work through access control system by VisionLabs. And here are examples of our customer analysis in retail companies and car showrooms. The system is able to recognize regular visitors and analyze customer flow for age, gender, and some other attributes. So here is the end of my first part. And if there are no questions here, I will continue to the second part about NIST.
Actually, there is a question. Elena writes a question, asks a question. How stable is the system if people are wearing masks, grow shaved beards, and etc.?
Okay. Yes, we so wearing masks is not a new problem for us because, as you can see, we have lots of projects in Asia where people wear masks because of the polluted air. So we adapted our algorithms to these kinds of occlusions too. And also recently NIST also measured accuracy of face recognition algorithms using occlusions. And as far as I remember, for now we are on the third or fourth place among all the competitors. So the system is quite stable in this. All of the systems that I talked about, for example, for access control, they work well with wearing masks, wearing sunglasses, beard, or something else.
All right, there are no any questions, so I think we can go to the NIST part of the talk.
Okay. So NIST face recognition vendor test. So here I will talk about a bit face recognition of how it works for everybody who understand what is this test about. NIST test overview will provide and talk about main challenges related to data and the algorithms on this test. So face recognition, how it works. The main goal of face recognition is to get information about which human is presented on the picture. There are two main tasks, verification and identification. In verification, we want to verify if there is the same person on two different photos or not. For example, it can be used in car sharing services. These services sometimes need to verify documents that are connected to the account and the person that is driving the car. Some services ask clients to make a photo on some period of time and compare it with one they posted during the registration. So in identification, we have a photo of person and we want to find him in database. It is called gallery. So we compare this one photo to many. For example, banks want to identify person in ATM. In this case, you don't have to take bank card with you. Usage of PIN code will be enough with your face. Now let's talk about pipeline for face recognition. In the first step, we localize face in the image, solve detection task, and find facial key points such as eyes, nose, and mouth. These key points are used on the second step, the normalization. Detected face is scaled, rotated, and cropped to match localized key points to predefine positions on the image. So the face looks frontal, like on the visa or in the passport photo. After that, on several regions of the normalized face, usually the region of eyes, mouth, and also entire face, we run a neural network, which task is to return as a vector or descriptor, describing the characteristics of our face. During network training, we force the descriptors for the faces of the same person to be similar or close to each other. This is a mated comparison. And the descriptors of different people to be different. This is imposter comparison. Thus, having descriptors for two or more persons, we can compare them with each other and get a measure of similarity, by which we will determine whether it is the same person or there are different people. This stage is called matching. And one of the most important steps in creating any machine learning system is to define how to measure the performance and the quality of the algorithm. Both verification and identification tasks can be considered as a binary classification task, so we can calculate standard metrics like true positive and false positive rate and plot the ROC curve. Basically, the false positive error is much more crucial than false negatives in case of face recognition. So to measure the quality of the algorithm, we should focus on the region of the very low false positive rates in the beginning of the ROC curve. This means that we measure true positive rate at fixed point of false positive rate. How low is the threshold for false positive rate that can be chosen? It depends on the database size or use cases that our client uses for our face recognition system. In some reports, also false non-match rate is used. For example, in NIST, they use this terminology. That is a simple subtraction of true positive rate from 1. So now I'm going to continue with the NIST test overview.
And before you start, can I ask a couple of questions about
yeah.
the story? So what's interesting here? How did the idea to apply for the participation in the NIST competition emerge? Who was the initiator of this?
We decided to test our algorithms for several reasons. First, the reason is that NIST tested the biggest independent test for face verification algorithms that covers different scenarios of face recognition applications. So we wanted to see a fair comparison to other companies on such a big scale. And the second reason is that if you want to get clients on the international market, your company has to be recognizable. Leading positions on such big independent tests open the doors for big companies all over the world, and this is our goal too.
Fantastic. And how was it being a tech startup to start competing with the big names in the computer vision and face recognition?
I think it was a big challenge. So when we started, we got quite good results in some tests and got even third place positions for some categories in this test. But also we saw results of best competitors and saw that there is a huge room for improvement of our algorithms. So it was some kind of additional motivation to make our products better. And also, it's very useful to find weaknesses of your products with help of huge report that NIST provides to its competitors. In some cases, it is hard to detect them on your own data, or in case of production usage, these weaknesses can be found on the very late stages of the project. So when we know about them in advance, we can offer a solution that solves our problematic cases. And I think like that.
Yeah, very clever, very clever. Great, thank you.
Okay, so let's continue with NIST. NIST tests all major global facial recognition systems and issues a 200-page report on the quality of algorithms working in various scenarios. And the main goals of these tests are, firstly, to state absolute accuracy for different kinds of images, and secondly, to state comparative accuracy across algorithms. So there are two main tracks in NIST face recognition. The first one is verification, and the second one is identification, as I already told before about face recognition tasks. So let's continue with the verification leaderboard. And this table shows the top performing verification algorithms measured on false non-match rate across several different data sets. So each column stays for the different data set. False non-match rate is the proportion of mated comparisons below a threshold that is set to achieve the fixed false match rate. In other words, false non-match rate is the error of not recognizing mated comparisons. So there are two people that are the same on the photos, and we say that they are not the same. And false match rate is error of false recognizing imposter comparison is the same person. So two persons are different, and the algorithm says that that is the same person. The algorithms are ordered here in terms of lowest mean rank across 4 data sets. The rank is here in brackets. So a mean rank is calculated using Visa, Visa border, mugshot, and wild test datasets. At this moment, we are top 1 vendor in 4 categories: in Visa, in standard mugshot test split, in for Visa border and border categories. I will talk about this test splits in details a bit later. Also, NIST measures not only accuracy, but also efficiency of face recognition algorithms, such as speed and template the size. On the vertical axis here, on the vertical axis, you can see the error rate, the false non-match rate, the fixed false match rate, so the lower is better. And on the horizontal axis, you can see template generation duration. So to the left means faster. Our algorithm is pointed here in a small red circle, this light blue dot. The color stands for template size. Heavy templates are marked as red points, and light templates are blue. You can see that our algorithm looks like the most efficient algorithm in terms of speed accuracy trade-off here. Our feature is that we send to the test those algorithms that are used in our products in production. So our clients can see real evaluations of algorithms that we develop. And you can see that most of the competitors demonstrate lacking reliable accuracy and production-ready resource consumption.
Yeah, when I saw this slide first time, I was really impressed. Yeah, I understand how your customers see the world using this visual.
Yes, it is quite useful diagram, but sometimes people don't look at it and look only on the leaderboard, and we want leaderboard to have an efficient algorithms in terms of efficiency too. Maybe sometime this will be it. Let's continue with identification. So the NIST has also a NIST identification leaderboard for algorithms. Here are sorted by the values in the only first column, so only the one test. Metrics here are false negative identification rate and false positive identification rate. They are similar to false non-match rate and false match rate for verification. So here you can see that for the identification task, we are in top 4 among all algorithms for this column. And also NIST has an investigation task. Here we are among top 3 vendors for investigation test. And I think I will continue and talk about it maybe in details further. So in terms of efficiency for identification task, we have also one of the most efficient algorithms. Here you can see the search time dependence on gallery size for top-rated algorithms. Blue line here stands for linear dependence of time on gallery size, and green line stands for the logarithmic dependence. We are the only algorithm that shows sublinear search among top competitors. Again, we send our production algorithms and show to clients real measurements, and linear search could be more accurate for us, but it also demands additional costs in resources for inference at our client side. So here is a small summary of our VisionLabs algorithm.
Just a second, Dmitry, there is a question for the previous slides. What are X and Y at these plots?
So X is the gallery size. Here, for example, you can see that gallery size is measured by hundreds of thousands, millions, and for example, 1.2, 12 millions. And the Y is the time that is required to search one photo in this gallery.
So gallery actually is a data set.
Yes, gallery is a data set, as I mentioned before. So in the identification task, we have a photo, and we want to find this photo in the gallery, in the big data set. So in, for example, huge companies, this gallery may be, or maybe some hundreds of thousands of people, or even millions of people, as we saw in our project in Singapore. There were 50 million people in the database. And searching on this database could be quite slow if we do a linear search. So we have to accelerate it, and we use sublinear search for this task.
And time units, seconds?
I think it was about. I think it was milliseconds. The seconds is too big for this measurement.
So milliseconds, yeah. And then we should apply this what we see.
Yeah, you can see that for different algorithms, this is a different scale. For example, some algorithms that are more accurate, they use even 7th order of magnitude here, but and use linear search. And we almost for every database size use a 4th level of magnitude here on the y-axis. So we are about, for example, three order of magnitude faster than this other top performing algorithm.
Okay. Okay. Thank you for clarification.
Okay. So here is a short summary about our algorithm and main challenges that are related to algorithms in this test. So we are top 2 in verification leaderboard, top 4 in identification, top 1 sublinear search algorithm for identification. We have very fast descriptor extraction speed. We operate in half-second descriptor extraction time on CPU. And also I will talk about the details about network acceleration in the section Trends and Technologies for Facial Recognition. Also, we have a very low memory consumption, only 512 bytes for descriptor size. And also we have optimized matching speed. So speed of comparison of the photos is less than 1 millisecond.
Okay. Dmitry, before we go deeper, can you please answer a couple of questions?
Yeah.
We see from your presentation a quite narrow gap in performance among competitors. What does it mean? How would you comment on this?
Yes, it's true. When you look at results for the first time, you can think that top algorithms have very close accuracy values. That means that there are different algorithms by different vendors that are now operating on approximately same level. Getting top 1 position is especially hard. But for some cases, for example, for banks with a huge database of clients, this difference on 0.01% can save a lot of money, and they will choose top vendor with the highest accuracy. And on the other side, as I already mentioned, taking into account this dense distribution vendors' accuracy, we focus not only the leaderboard position, but also the second challenge for us, the efficiency of our algorithm. And as you could see, we have one of the fastest algorithms with very low descriptor size. This efficiency helps us to make our solutions cheaper in terms of usage of software and required hardware for our clients. I think, yeah, okay. That's all.
And in identification leaderboards, VisionLabs is number 4. So do you see a potential to do better?
Yes, of course. There is a huge room for improvement. For example, as I already told, if we did not restrict ourselves to sublinear search, the results could be better, a bit better. Also, identification leaderboard is now focused only on the test split of mugshot images, the only 1 column. I will show these images a bit later. So, for example, if you train mostly on this domain, results could be better. And of course, we continue our research of our face recognition networks. And if you look at whole NIST test report, you can see that there is a huge improvement for the last 2 years on an order of magnitude in face recognition accuracy. So who gets this improvement faster, those will get top rank positions.
Yeah, and we are coming to my last question here. So can you tell us what does it mean to be better at this competition? To have a better research team, or to have more practical experience doing industrial projects and being quicker, or it's just a matter of luck or serendipity? What do you think?
I think all of these companies are really. We have a team of talented researchers that do their best to improve our solution. Also, it is important to have lots of computing resources. More resources you have, more ideas and hypotheses you can check. Sometimes a bit of luck takes place when two competing algorithms perform very close, and draw curve on the RBC curve on in the point that comes to leaderboard for one of these algorithms bursts forward, losing on the other points maybe of the curve that do not count in the leaderboard. So yes, it's a bit of luck sometimes when competing of two algorithms. So sometimes to be top one confidently, you have to beat other competitors with some margin, some gap, which is a really hard task for us.
Yeah, thank you. So let's go deeper into the essence of deep learning.
Okay, so now I will talk about main challenges that are related to data, and talk about main data sets that are used for NIST verification. So there are 5 main data sets. 3 of them are cooperative. This means that persons are looking to the camera. Non-cooperative data set, these photos are wild capture. And also there is a cross-domain test when NIST makes verification pairs from 2 different domains, from visa and border. And I will talk about them now. So before this, here's a short history of our submissions to verification test. In total, we have 9 submissions with average 2 submissions per year. At this moment, vendor can submit new algorithms with period of 4 months. And our first submission got 3rd place in several categories. And in 2018, our algorithms finally started to get top one positions in mugshot and wild datasets. After this, we regularly showed the best results for cooperative datasets such as mugshot, visa, and in 2020 on new hard dataset visa border, visa border was in 2019. And as you can see here, that after 2018, we didn't get top positions on the wild split, and later I will discuss possible reasons for it. And now we have, as I already mentioned, top ranked position for 1 submission on 4 datasets at the same time. And now I'm going to talk about each test split in a bit more details.
Just a quick comment. I remember that you joined VisionLabs in 2017. When I look at the table, I see some improvements since that time.
Actually, I personally started to do algorithms for NIST submission since 2018, and the first 2 submissions were made by our team when I didn't join. So let's talk about the this dataset. Here is an example of images in this dataset. The pose is generally excellent. The images are fixed size. There are about 100,000 people in this dataset. So the main challenges here are that the persons are from greater than 100 countries. And also the images are of persons of all ages, including adults and children. So why is this the challenge for modern face recognition algorithms? Here is an illustration of why it is a challenge. Here is distribution of training images from 2 large public data sets. in terms of nationality on the left, race on the right, and age distribution in the middle. You can see that Caucasian middle age persons dominate in public data sets, and lack of other races and ages results in poor face recognition results for these domains. So how can we solve this problem? One of the most effective ways, and also one of the most difficult, is balancing your data with additional data collection. It is one of the most important thing for face recognition algorithms. In this case, it is important to use all of the possible sources. Of course, we use public data sets, but also we got some raw data from internet and our partners. For some cases, we create internal data collection setups, but we need not only the raw data, but also labels. It is convenient to do labeling with crowdsourcing. For some project, we use Yandex Toloka and Amazon Mechanical Turk. Both of them allow you to upload simple tasks and find people that are ready to do them for a small fee. But in significant part of cases, we cannot give our data in public, so we label it by internal labelers. It is more expensive, it's slower, but we have no choice for data with privacy requirements. But for some cases, accuracy by internal labelers is higher in comparison to crowdsourcing.
Yeah, and the data collection and data processing, labeling is really a pain in the ass, and we probably will make one of the events and invite people from companies which provide such services.
Okay. It will be quite interesting. So also for balancing the data sets, additional face attributes can be used. We have our own neural networks that can predict such attributes as gender, age, ethnicity, and emotions. By using these attributes predictions, we can estimate and control the balance of different subgroups in our training data sets. You can see here that domain of raw data is crucial for attribute networks too. The accuracy is much better for cooperative frontal images in comparison to those that are captured in the wild. But they are also quite useful. Here is one of important graphs from large NIST report that shows dependence of the error of false non-match rate on birthplace of persons in the visa dataset. So NIST has ground rules for birthplace. Errors at fixed point of false match rates are colored with red and blue here. On the right, you can see latest public submission. So the research paper with all details of which is published. And they use public data that I saw before, showed before. Also, authors have open source code for training their models in GitHub. You can see that solution trained on public data set demonstrates worse performance on profiles from countries of Latin America, like I think Argentina, Peru, Brazil, also Mexico, Venezuela, Ecuador, and so on. So by balancing our trained data with the external data sets that we collect, we reduced the false non-match rate error for these sub-regions. As you can see on the left, this is our submission. Here you can see performance of our and public algorithms on different age groups. So false face recognition on children is still a challenging problem for all the algorithms. But you can see that with our effort of balancing age distribution and trained data, we reduced error on very young people more than twice in absolute value than the algorithm trained on the public data set. And here is a final leaderboard for visa, including false non-match rate values and also descriptor extraction time in milliseconds and descriptor size in bytes that measure efficiency to this of these algorithms. This is how we want the leaderboard to look like with these efficiency terms. Here we have the lowest error among all the algorithms, and what for me is even more important, we are much faster than anyone in top 10 and have very compact descriptor size. So a few words about accuracy. You can see that accuracy is very high, more than 99% with false match probability 1 in a million. And distribution of error values is quite dense, but it's still good test for measuring cooperative false recognition error, because if you compare top 10 and top 1, you can see that top 1 has more than 40% relative improvement in reducing the error, which is quite a huge gap for face recognition systems for today. And also, public solution was added to this leaderboard to show you the current state of public face recognition, open source face recognition, and you can see that the solution really works well. So accuracy is still more than 99%. So the other data set is a Maxio data set, is similar, quite similar to Visa, but it has different distribution. There are about 1 million people in this data set, so it is quite huge data set. The images are of variable size, but it really doesn't matter. And the main challenge here is that dataset contains pairs of the same person with age difference up to 14 years. This is a real challenge for today face recognition algorithm. On this graph, you can see dependence of false non-match rate error on time, difference between photos taken for mated comparisons. Here are different curves for different genders, so female and male, female with a solid line and male with a dashed line, and also for races, the black and white. So false match rate here is set globally on the entire imposter set on the value 1 in 100,000. And you can see that aging makes face recognition more difficult, and error increases in general when we increase the time difference and when we go to the right of this curve. Also, you can see that absolute values of false non-match rate for our algorithm are much lower than for algorithm trained on public data. One of key elements here is our goal to collect most diverse profiles in our training data, including different ages of the same person. And finally, of course, you can see that there is a huge, big room for improvement on this task. Another graph here is about the demographics effects and the false match rate on these subgroups. So also, although you saw that black test splits have lower false non-match rate error than white test splits when the threshold is set. So you can see that these red curves are lower than blue curves, so the error is lower. Black test split has higher false match rate for most of the algorithms. This is a common problem, and also especially women splits have higher false match rate for the set threshold on the data set. So this is still unsolved problem, and this could be, I think it could be done in the future.
Dmitry, there are a couple of questions here. Yes. I think that some of them relate general to the data challenges with data, but one is about the slide which is currently on the screen. So Elena asks a question: how come that the error for white is higher, although the data set contains less black people?
Yes, this is the good question.
The slide before, yes.
Yes, you can see here that error for black is lower, but this is only the one type of error. This is a false non-match rate error. If you can see, if you see on this second table too, so what is this table? Here are false match rates. So there are other kind of errors in face recognition that are much more crucial. And you can see here that false match rates for black are higher for most of the algorithms than for wide data sets. So we have lower false non-match rate at fixed threshold, but also we have lots of false positive matches, and that is the problem. So in general, we should tune our face recognition algorithm to have lower false match rate. But of course, when we set the threshold lower, the false non-match rate increases. Okay, I think I can continue. So here is the mugshot leaderboard. Here is the same picture. We are top one solution, and we are a bit of luck here for being top one. We are the most effective algorithm, and you can see that this test split is a bit more saturated than Visa. So there is only 2% relative difference between top one and top 10 solution, and public solution also works quite well here. So the most hard data set for cooperative face recognition and NIST test is the border data set. It has about 1 million persons in this split. Here are the examples of how the image can look like. So main challenges here are the same for the Visa. So there are lots of lots of persons from greater than 100 different countries, greater than 100 countries. Also, there are some different roll, pitch, and yaw angle variations, which is hard for face recognition. And also, face can be underexposed. There can be some perspective distortion due to close range images, and some faces in this data set are partially cropped. And you can see here that this is the highest error among all cooperative data sets in this test. So this is the hardest test for today. And here you can see a huge gap between top 1 and top 10 solution. So there is about 30% relative difference. So this is quite good and challengeable test for modern face recognition algorithms. What is more interesting is this Visa border data set. I talked before about the border, I talked about the Visa, and what NIST makes, it make comparisons of 2 different domains. So the comparisons are of Visa-like frontals against border crossing webcam photos. So the number of persons here is also about 1 million. Also, there's a huge distribution of persons countries, and the main challenge here is cross-domain verification. And here we are also top 1 with a quite huge gap from other participants, also most effective. And here also you can see that the relative difference between top 1 and top 10 is about 30%. So this data set is not doesn't look like a saturated one. Even the accuracy is quite good. And finally, the wild data set. This is the hardest data set among all NIST tests according to the false non-match rate errors values. So this is quite small in terms of persons. There are only some thousands of persons. So in previous data sets, there were millions of them. So main challenges here are that the images the images resolution varies very widely. Also, they have wide yaw and pitch pose variation, and also faces can be occluded, including hair and hands. So this is a wild leaderboard. Here we are not on the top 1. Here we are on the currently we are on the 13th place, but for this data set, false non-match rate error is much bigger than for cooperative data sets. Accuracy is about 97%, as you can see for almost all the algorithms. We observe that error in this test become saturated near value 0.3. and there is less than 5% relative improvement between our solution and top one solution. So maybe in this data set, there's a bit of luck to get higher positions. The reason can be difficult phases in data set, for example, that are impossible to recognize to any of the algorithms. So the accuracy of 97% is a limit for modern algorithms. And also this situation can be observed if there are some incorrect labels in the data set, we don't know about it.
But here, if we look at the descriptor extraction time, your algorithm is the best.
Yes, we still we're trying to be the most effective algorithm, and here also we are the best among top players, but the accuracy is not on the top position here.
That's a matter of metric. So what would you like to have? 0.293 with 972, or 0.3006 with half of that's
yes. So the difference is very small, but unfortunately this rank position is in the total ranking of the algorithm. So our bad rank on wild leaderboard is the reason why we are now in top 2 position in general leaderboard and not on the top 1. So the only data set that looks challengeable for us is the wild leaderboard.
Yeah, and one more question, technical question from Synap. Sorry if I pronounced it incorrectly. You maintain the same descriptor size for all the data set types, right?
Yes. So most of the algorithms do the same descriptor size for all the test data sets, and not only the descriptor size, but also the same algorithm is evaluated on all the test splits. So here are some additional images of mugshots. These are taken from the mugshot gallery examples from an identification tasks. So in pairs of photos is the same person. Photos are taken at different moment of time, and these images are from gallery, and these images are from probes in identification tasks. So here, for example, is an example of profile to mugshot matching. So we have a profile image, and we want to, using this probe or profile, find this person in a frontal mugshot gallery. This is extreme case for identification, and for some algorithms this case is almost impossible. And another test set for identification is webcam to mugshot matching. Photos from webcams are quite blurry. They have bad lighting conditions, and sometimes are cropped, as you can see here. So this can be a challenge for face recognition algorithms too. And here again is the leaderboard of different algorithms in the test sets. This first one is original mugshot to mugshot comparison on gallery size of 12 million. Second stands for reduced gallery size to 1.6 million. And third stage for webcam to mugshot, and you can see big degradation of performance when we use bad quality images for search. It becomes even worse when if we use profile photos, as in the next column. You can see here, and for some algorithms, this you can see that it is almost impossible to do profile to mugshot matching. And the last two columns stay for visa border cross-domain comparisons and mugshots with time difference more than 12 years, the same as for verification test before. So this is the end of this section. So if we have any questions about it, I can answer them now, and then I will continue with a survey about face recognition.
Yeah, there are questions related to data sets and challenges with data.
Mm-hmm.
Anna asked a question: what is the size of your training database?
Size?
Size
We
of your training data.
of course we cannot tell the total size of our training database, but you can see, well, we can say that there is several millions of photos.
Okay. Question from Slava: which data sets exactly from public ones did you use? Public, do you use public data sets, data sets, and which public data sets do you use?
Actually, we didn't use public data sets as is, because there in public data sets there are some problems with labeling. So they're quite noisy, and I will show some examples of them later in the next section. So what we do, we take public data sets and we re-annotate them with our instruments, with our labelers, with our neural networks. And so you can say that almost all of the public data sets that have a large number of photos and persons are used in our face recognition learning pipeline.
Thank you. And the question from Zainab, sorry. Do you consider using GANs to tackle the problem of data, general adversarial networks?
Actually, we tried to use GANs for some specific task, and it helped a bit, but it is not related to NIST. So I can talk about it shortly. So, for example, when we want to make face recognition on domains that are not presented in training data. For example, we train our networks on RGB data, and we want to do verification on infrared cameras. Infrared data is unavailable in such amount like RGB. So one of our solutions that we tried to do was to generate infrared images from RGB and to improve our recognition on infrared cameras by this approach. And for some cases, it helped.
How do you handle bias present in public datasets, e.g. in CELEB A?
About the bias, so I already told before, we try to collect specific external data from specific regions, from for age groups, for countries, and by adding this type of data to our whole data set, we try to reduce this bias and long tail distribution. This is the most effective way for us.
Thank you, Dmitry. There are no questions related to this section, so I think we can proceed.
Okay. Yeah, I can continue.
Do you read this? Can you read this question?
I need to open the chat, I think.
Okay, I will read it for you. So maybe we can answer this question later, not right now, but let me read it. Do you know the origin of the competitors? I would guess that Chinese companies might have access to huge databases rather than European ones.
Yes, it is. You're right in a bit. So, for example, if we open the general leaderboard, I think on verification. Sorry for this. Oh, we can see it. Here. So yes, the origin of many of companies such as Deep Green, such as I think Dehua, the developer of cameras. So DeepGlean, SenseTime, and some other companies like MacV, or also known as Face++, are from Asian, have Asian origin. And also, if you look at the report in details of these algorithms, you can see that Asian algorithms perform on Asian test fleets much better than other algorithms that were developed, for example, in Europe or the USA. So we assume that they have access to their local data, and this is quite difficult to compete with them because we didn't have such amount of their local data.
Thank you.
So now I can continue. A few seconds. Yes, here. So now I'll talk about the trends and technologies for facial recognition in computer vision, and also mention some details about our NIST submission that we made before. I will talk about, firstly, the main section will be about deep learning revolution and advances in face recognition with deep learning. And finally, a few slides about research challenges for the fair and reliable face recognition. So let's start. Advances in face recognition. So there are three main topics: the face detection, face normalization, face descriptor for representation learning, and I will cover them sequentially. There is just a reminder of how this works. So firstly, we do detection, then we do normalization, and then we extract the descriptor. And here is a graph that shows the substantial growth of research papers in deep learning era. So you can see here that face detection, face preprocessing, face normalization, and face descriptor papers are published in a large amount every year. So it provides good improvement in end-to-end face recognition. So let's start from the advances in face detection. Basically, face detection methods are based on techniques that are used for classic detection tasks. We can see here improvement of detection algorithms and 3 times between one of the first deep learning detector faster CNN and DPM detector based on non-neural network approaches. Here you can see that even after deep learning revolution, there is a huge, more than 3 times progress in terms of accuracy. So metric here is mean average precision on COCO dataset. And this also can be seen in face detection algorithms. Here you can see a huge gap between the DPM detector that I mentioned before and other first neural network-based face detector on the precision recall curve on wider face hard data set. So this detector is MTCNN. Also, new face detectors are being published and released, and there is still good improvement here for the next generation of detectors. This improvement can be easily visualized on this example called the world's largest selfie. This is how traditional Violo-Jones detector works on this photo. And this is, for comparison, how one of our VisionLabs detectors work. You can see that deep learning detectors find much more faces and much more small faces on this image. So why this revolution happened? The first reason is data. Here is a list of most popular face detection data sets taken from recent survey on face recognition. So the main data set here is wider face. This data set has subsets for training, validation, and tests. Each subset has 3 difficult levels: easy, medium, and hard. And the wider face has promoted the community of face detection in the past few years, which provides a large number of training data and challenging test benchmark with large variations. So the second reason is developing new neural network architectures and methods for face detection. Here we can see main publications for face detection algorithms during last 5 years. So blue colors here stay for the multi-stage detectors and gray stays for single stage. You can see here that there is trend towards developing single stage detectors today. So what's the difference? Multi-stage based detectors first generate a number of candidate boxes, like here, and then refine the candidates by one or more additional stages. The first stage employs sliding window to propose the candidate bounding boxes at a given scale, and the later stages reject the false positives and refine the remaining boxes with higher resolution. In such regime, the cascaded architecture is naturally and an effective solution for the course-defined phase detection. So, in contrast, the single-stage methods accomplish the candidate classification and bounding box regression from the entire features map directly, without involving any proposal stage like in multi-stage detector. So these single-stage detectors can be much more faster than a multi-stage one. So what's the difference between the phase detection and object detection? Modern phase detection algorithms are based on single-stage object detection ideas, but with some domain-specific improvements. Almost all of them cope with small average phase size, the large pose variation and occlusions, and also speed requirements. So if we have small phases, one of the first solutions is very simple. If we have small phase, let's make small anchor boxes on our detector. So anchor boxes are the bounding boxes on the feature level, feature map level, where we expect to be an object. So if the object is small, okay, let's do the anchor small and find small phases. So this idea was developed in S3FD detector, single shot scale invariant phase detector, one of the most popular single shot baseline detectors. Additional idea here is a multi-scale prediction. Phase boxes are generated from different feature maps. So small phases can be detected on the early stages here. And then information from all layers is aggregated and final prediction is made. So in lots of other works, try to improve this architecture with techniques and some techniques and modifications. One of such techniques is hard negative mining. Why we need this? Because large proportion of candidate boxes originate on small scale, resulting in many small scale false positives. So there are many areas on the image where the small face is predicted, but it's false positive. So we need to cope with it somehow. And there are different techniques to cope with it. Some of them are connected with hard negative mining. Also, new loss functions were implemented, such as focal loss, and technique as max out was presented in S3FD detector. I will not tell about the details here. If someone wants, he can just read the paper and find the solution there. And another problem of phase detection algorithm is demonstrated here. In the left, you can see low resolution crops from the picture from the right side. Looking only on these crops, it is very difficult to classify what is shown there. But if you look on the right photo, we can easily distinguish that there is an arm on the bottom and face on the top. So why it becomes easy for us? Because we see the context. So we can add context to our neural network to make predictions better. Firstly, context is automatically added on deeper layers of neural network due to increasing receptive field of convolutional filters, but it works only on deep layers. So context addition on first stages, on the early stages of the neural network can be added by feature pyramid networks with backward or reciprocal connections. After extracting high-level information on deep layers, we can pass these features backwards to add context knowledge for our earlier feature maps. For example, high-level feature may contain information that there is a small human body in some region of the image. So early stages can better predict small face up to it. And finally, now let's talk about the speed requirements for face detection. Face detection is required for face recognition, but we cannot do it during long time. Here you can see that huge progress in face detection accuracy comes with a performance cost. Simple MTCN detector works much faster than original S3FD detector, so it cannot be used in production as is. So what we did, we accelerated this S3FD detector with the usage of those techniques and methods that I mentioned before. And core of our solution for one of the previous NIST submissions were single-stage phase detection based on S3FD architecture. So we changed the backbone. We used fast mobile net style architecture to make it much faster. We also did extensive hard negative mining. We added a context via feature pyramids and also used some additional training data that we have. And on the right side, you can see that our detector, purple, works approximately on the same level as original S3FD detector, green. But according to the table, you can see that it works even faster than MTCNN. That was our previous production detector, especially when there are many different phases on the image because of single stage detection in our algorithm and cascaded multi-stage detection in MTCNN. So here is how we did a detector for one of our previous submissions for NIST data test. So here is a small summary of for phase detection. The main challenges of phase detection are small phases, so they are often impossible to detect without context. There are large pose variations and occlusions, so we need data, and also runtime efficiency. We need to accelerate our phase detection algorithms. And I will continue with the advances in phase normalization. This will be about the key point localization. So given the detected phase region, phase pre-processing aims to calibrate unconstrained phases to a canonical layout for facilitating the downstream tasks of recognition and analysis, which is an essential intermediate step in the end-to-end phase recognition system. So in order to remove the scale, rotation, and translation variations, phase alignment employs spatial transformation to calibrate phases to a predicted canonical layout with the help of facial landmarks. The development of methods for phase preprocessing is presented here. I will talk about some of them. Here's a table of mostly used phase landmark datasets. You can see here that they use different set of landmarks. Sometimes it can be a challenge to train on all of these datasets. So the most challenging data here are phases with huge variation of angles and occlusions for unconstrained phase recognition. And here is the performance comparison of different landmark localization methods on the one of test datasets. It's called 300W. So the metric here is normalized mean error. So lower normalized mean error indicates better performance. And you can see boost performance with deep learning methods, but in the last few years, performance on this data set looks like a bit saturated here. Now let's talk about main methods for landmark localization. So the first one is coordinate regression, the second one is heat map regression, the third one is 3D model fitting. I will focus mainly on the first one because it is more appropriate for production use cases in face recognition systems. So the coordinate regression based methods regard the landmark coordinates as the objective of the regression with neural network. So this is the architecture of the neural network. You pass the detection as the input, and it outputs to L points of landmarks. So if we have landmarks, we predict 10 float points, 2 points for each coordinate. In other words, These algorithms focus on the nonlinear mapping from the face images to the landmark coordinate vectors with neural networks. So for coordinate regression tasks, we can take standard regression losses such as mean squared error or mean average error, but also some new losses were designed for face landmark localization. One of the most popular among them is wing loss. It is a parameterized loss with two parameters, W and epsilon, and basically it is linear loss when distance between predicted landmark and ground truth landmark is more than W here. And here is a nonlinear part, logarithmic function, when distance is smaller. With addition of nonlinearity, we can modulate the gradients from landmarks with small errors and additionally force them to be closer to target positions. I think, yes, the coordinate regression is #1 solution for face recognition pipeline because it is fast and simple, but I will shortly mention some of the approaches. So the other method is a heat map regression that uses hourglass stacked network. This architecture is widely used for such tasks as pose estimation, which is quite similar to face landmark localization. In pose estimation, we also look for key points, but instead of face, they are localized in the body joints, and I will not talk here about the details for face recognition. Also, the other solution is 3D model fitting. So we can make a dense 3D morphable model and use it to model a 2D face to a 3D shape. The regression network estimates the parameters of 3D shape and projection matrix. And then the 3D shape is projected onto the image plane to obtain the 2D landmarks. This can be quite longer than traditional some key points, but some researchers also use these approaches too. Also, we can normalize faces without relying on facial landmarks. Several other methods can still generate aligned faces. Some of them, most of them use so-called spatial transformers on the alignment network and allow to learn the normalization of the image and the representation network that generates the descriptor end-to-end. And also, finally, in the uncontrolled environment, pose variation is a serious issue for the face recognition, and to eliminate the pose influence, such technique as face frontalization aims to synthesize identity-preserving frontal faces from non-frontal views. So in some cases it works, but this is not the case today for the production, I think. And recently, the high-quality image generation has made great progress due to the generative adversarial networks that we already mentioned before. Moreover, some approaches even try to combine generative adversarial networks with the 3D face model to exploit the facial prior knowledge of face synthesis. But this is kind of experimental work, I think. So there is a short summary. Main challenges for landmark localization are facial variations, such as extreme blur, occlusion, low illumination, and so on, and also runtime efficiency. And because of runtime efficiency, most of algo systems use coordinate-based face landmark localization algorithms in production. And finally, I will talk about the third part, about advances in face descriptor. This is actually the part that I'm focused on in when I'm working in VisionLabs, and my team works on the construction of face descriptors from the aligned faces. There are three main face descriptor learning components, such as data, loss function, and neural network architecture. So we talked about the data a bit before. There are lots of train and test data sets with large number of identities and images. So the first problem is that data sets are not clean enough and contain lots of mistakes. Here are some dirty profiles shown. Images in rows stand for one class according to labels. You can see that there's some mistakes that are easy to detect, like this one, they have different, for example, gender. And also there are some that are quite hard to detect even for human. Actually, modern face recognition systems perform even better than human. So human labeling is not the only one we should rely on when we label our datasets. Moreover, the problem arises when we try to combine several datasets into a new one to obtain big dataset. Datasets overlap over identities, and if we don't find all the overlaps, the addition of new data can even worsen the accuracy of the face recognition algorithm because of incorrect labels. And the second problem is that data is imbalanced. Yes, yeah, I've already talked about it before. So if we talk about neural network architectures for face recognition, so basically general ImageNet-like architectures like ResNets, CNNets are good baselines for face recognition and are widely used in face recognition papers. And the good ways to accelerate these face recognition networks are common for ImageNet-like tasks. So we can use some depwise and group convolutions like in such architectures as MobileNet, ShuffleNet, and ResNext. Use some inverted residual blocks like in MobileNet v2 and EfficientNet by Google. So neural architecture search for face recognition could be reasonable. And also it is important to use knowledge distillation techniques to obtain maximum accuracy for these architectures. So now let's talk about the optimization task that is formulated for face recognition. Here on the left is the example. Yeah.
Can I ask a couple of questions before we go to the loss function?
Yes, of course.
Elena asks about very large selfie demo. Is it possible to do face recognition on this, or it's only for face detection?
Can you tell me about which slide is it?
It was there in the very beginning when you told us that VisionLabs algorithm detected more faces than previous algorithms. Yeah, here.
So here I showed that VisionLabs detectors, yes, detect more faces, but I don't quite understand what is the question about face recognition here.
Can you do any face recognition task on such a, I don't know, what is it?
I think it means that if we find these faces, can we still recognize them if we put these images to the face recognition? Actually, it depends on the image resolution. So we analyzed our face recognition algorithms and the dependence on the input image size. So if the face is more than, for example, about 30 pixels, it can be well recognized for modern face recognition algorithms. If the face is smaller, it can be a degradation of accuracy.
Yeah, that was the question. Like faces are small, what can we do? Another question is from Zainab. Do you use the same architecture to process the different data sets? Because for visa or border, for instance, you know that the image will contain only one face.
Yeah, our task is to create one unique neural network or one unique algorithm that works well on all the different data sets and all the scenarios, because developing different algorithms for different scenarios, we don't think that this is a good solution in terms of making a whole face recognition system.
Yeah, thank you.
Okay, so now I'll return to the loss functions about face recognition. So here on the left, yes, as I told, is an example of two-dimensional descriptor space learned by the neural network for simple task. of classification, different identities of the trained data set. Different colors here correspond to different identities. Here is a problem because for face recognition, we need descriptors of the same person be much closer to each other than to descriptors of other persons. So we should modify simple classification loss function to force descriptors to look like they are on the right side here. This can be made by applying margins to learn discriminative features in the descriptor subspace. This is a basic idea. So how this, there is a bit of formulas. So how we do that in a mathematical way. Here in top, you can see the standard cross-entropy loss function for learning of classification. I hope everyone is knows about it here. So firstly, we manually project all descriptors to the hypersphere with radius s that is here. It is centered to 0, so we remove the bias. And S is a hyperparameter for learning. It gives us an ability to do classification only by having descriptor direction X and directions of the linear classifiers W. We call them learnable centroids of classificator. This projection operation stands for normalize softmax, that is the second row. And classification now can be evaluated based on the angles theta that are shown here. Then we add some kind of margin to the classification function. We simply reduce the output value for the target class to make classification task more difficult. This reduction is made by introducing margins M1, M2, or M3. For example, margin M1 means that we force neural network to have the angle between descriptor X and target centroid W to be M1 times less than to any other centroid. So the features become more discriminating in the descriptor space. It can be easily observed on this classification bounds in angle space. For two classes and softmax, it simply divides the space on two areas. By adding the margin, we deform this classification bound, and all samples of class 1 are classified correctly only if they are in smaller blue part of space. So the classification task becomes much more harder for the neural network to learn. All three different margins were introduced separately in 3 different works called sphere phase, cos phase, and dark phase, and all of them perform much better on face recognition tests than simple softmax classification, and are a good choice for learning of face recognition neural net as a baseline. And also now let's talk about how to train efficient algorithms in terms of speed accuracy trade-off. So one of the most useful options for this is knowledge distillation. This illustration is of how it is traditionally used. Assume you have a big slow model that performs good, but it's slow. It's called a teacher model. One of the first steps on the first step, we train a teacher model to solve the classification task using original labels that we have in our dataset. Here, a loss function is simple cross entropy that takes classification logits of the network and the one-hot encoded labels as inputs. Then we remove this loss function, take the teacher network, freeze its weights, and create soft targets. We simply apply softmax to the classification logits divided by a factor t that is called temperature. In result, we obtain soft targets that are soft improbabilities of the teacher network outputs. We freeze the teacher network and train the fast and light student network for the same classification tasks, but instead of using original labels that were one-hot, we use soft predictions of the teacher as new labels here. So that is the trick of knowledge distillation. So we adapted this technique for usage in face recognition learning. The situation is very similar. We also firstly trained deep teacher architecture, but the difference is that now we have classification logits that include usage of margins that affect in penalizing of target probabilities. These new logits can be used for creating new soft targets and then can be used as new targets for the student network, the same as for standard knowledge distillation. And here are the results of usage of several distillation techniques to our case with mobile network. Here we use the combination of sphere phase and distillation loss for ResNext 50 as a teacher and ShuffleNet architecture as a student. So margin-based knowledge distillation significantly reduces the gap between student and teacher networks on unconstrained test data sets such as LFW and IGBA. You can see the difference here. And also another problem that we solve is compatibility of two face recognition models. For example, if you have a deep and mobile neural networks, deep neural network as teacher and mobile neural network as student, it is reasonable to have an opportunity to match descriptors obtained by different models. So the descriptors are on the same descriptor space. So simple solution here is adding a term to the loss function that minimizes distance between descriptors on the same image for teacher and student networks. Here are the results with adding this loss on descriptors. It doesn't provide any accuracy degradation relatively to margin-based knowledge distillation in the table, as you can see here. Here we compare our approach with simple MSE loss without knowledge distillation and show that usage of knowledge distillation is really useful in this task, and you cannot use only the MSE loss. And also we show that addition of MSE loss really provides the compatibility of two models. In the bottom table, we see that if we match teacher and student descriptors, the results became even better. So in some cases, we can use mobile networks approximately without any loss in accuracy in comparison to original teacher model. So in this case, we extract the descriptor for probe with the student network, and the gallery is extracted once with the teacher network. And also we compare our approach with simple MSE loss here without knowledge distillation and show that usage of knowledge distillation provides better compatibility than using only the MSE loss. That can be shown in the values here on the HB. And talking about the runtime efficiency, we try to use all available mechanisms of neural network acceleration. We accelerate neural network inference on a wide range of platforms with help of our Flower framework. We use neural network quantization that helps to speed up the algorithms. And also we use special neural network processing units and optimize our neural architectures for inference on these devices, on these chips. I think that's all for this section. And finally, main challenges as a summary of phase descriptor learning. So the first one for the data is imbalanced data in noisy labels. It's a very hard task, and we should fix it somehow. Loss functions for discriminated features should be implemented. So of course, we implement our own loss functions because for getting top rank position, we cannot use public loss functions, and we implement ours, but we use public loss functions as the baselines. And also the runtime efficiency is a challenge for phase descriptor extraction. So this will be the end for the first main part of this, and I'm going to continue with research challenges for fair and more reliable face recognition if there are no questions at this point.
Yeah, there is a question from Slava. I think you mentioned that, but let's read it. So, do you use single CNN or use multiple CNNs, e.g., ensemble techniques?
Actually, we for whole phase system we use multiple CNNs because we use CNN for face detection, we use CNN for face landmark localization, and CNN for descriptor extraction. And for all of these tasks, we use one CNN per task.
Okay. A question from Mikhail. Is your NIST FR algorithm the best one you have, or you have more accurate but slower algorithm, teacher model, which you use for data labeling or other internal tasks?
Yes, we have better algorithms that are a bit better than those that we published to our NIST test. So yes,
Okay.
they're used as teachers.
Yeah, thank you. Thank you. I think we can go on. There are no questions at the time, so.
Okay, I think I will describe this section quite short. So here are main topics that I'm going to talk about. The face recognition problem, age and race bias, I've already mentioned before in NIST section, and also liveness technology for reliable face recognition. So shortly, there is a problem for face recognition like age bias. As I already mentioned, face recognition algorithms have problems while working with children and most adult people. Here, red regions show high false match rates comparison relatively to average false match rate across all data set. And it should be taken into account, for example, when installing for face recognition system in school, for example. Additional adjustment of face recognition system is required to prevent large number of false positives in this case. And also, we can say the same thing for face recognition systems working in different regions. Here, red squares also correspond to regions where false match rate is increased relatively to average level. Most of algorithms perform well on Caucasian people, so they're white squares here on some, for example, for European people, and have problems with Black and Asian races. So additional adjustment is required when you install your face recognition systems on in these regions. So some of new papers are published about these problems, but I expect a huge improvement in this face recognition problems in the nearest future. And also, I would like to talk shortly about the liveness. So as soon as we start using facial recognition in some scenarios, ATMs, face payment, or something similar, the question immediately arises of the possibility of hacking the system or spoofing the system. For example, by showing a photo or a video of another person. The easiest way to protect this is two-factor authentication. For example, you can use your face and PIN code, but you can also increase the stability of face-only authentication. The task of determining whether a person is alive or fake is called liveness. Here are examples of real and fake images. Liveness is a very difficult task, so we develop algorithms in several directions at once to find a solution to it. So here are some of them. The first solution is liveness using a depth map. Depth map is an analog of a normal image, each pixel of which is encoded with the distance from the camera to the object. For example, a flat sheet of paper on a depth map has the same color because the distance is the same. At the same time, the person's face is quite distinguishable. So liveness on the depth map allows you to easily cut off flat objects. So this type of liveness is resistant to attacks from a sheet of paper or a phone screen, but it can be hacked with a personal 3D mask, and also depth camera are often expensive, so clients don't want to buy them. A cheaper option is to use an infrared camera instead of camera with a depth map. An infrared camera works in a different range of light waves that are invisible to human. Therefore, it can also be used in the dark, illuminating a person with an infrared flashlight, the light from which human also does not see. An interesting feature of infrared cameras is that images from different device screens are not displayed in frequency spectrum of infrared cameras, and therefore this immediately prevents all attacks using screens. The lack of infrared cameras, it often happens that different cameras produce different images. And this requires retraining models for every new type of camera. And here is a small demo of how it works. This video shows an example of the liveness system based on two cameras. visible spectrum on the left and the infrared on the right. You can see that eyes shine in the infrared camera on real people due to the fact that the camera shines a flashlight. The printed sheets do not have this, and they even visually look different in infrared spectrum. And also, laptop is not visible. The laptop screen is not visible here. The same is with the phone, and also printed faces cut out along borders are also not a problem for this system. Also, we have multi-atomic liveness. This is another liveness technology. It is based on user interaction, namely the instruction to do a certain set of actions, such as blink your left eye and open your mouth. This approach is resistant to a variety of attack options, as it implies controlled movements. However, it's quite uncomfortable as it requires serious user involvement in the process. So there were just some of approaches that we are trying as part of our work on liveness. And also, by knowledge of the NIST face recognition tests, there are also some anti-spoofing challenges for liveness detection. Our algorithms got top 1 positions in last 2 years on CVPR face anti-spoofing challenge for multimodal and single model attacks. So for single model attacks, only RGB image are used as input to the algorithm, which is much more difficult. But also we had top 1 solution. So I think it is close to end of my talk. Here is some additional information. We have, if somebody wants to join our research team, you can contact us via email. We have open intern positions for beginners in computer vision. Feel free to contact us. We expect candidates with strong technical background, knowledge of basics in computer vision and deep learning, preferably with some experience such as pet projects in computer vision.
Okay.
And yeah,
before you start the next slide, I would like to ask a question that will relate to this slide. So VisionLabs initiated Computer Vision and Deep Learning Summit, and you will talk about it a bit later. And now VisionLabs interacting with a global community of scientists and practitioners in computer vision. So can you provide us with your opinion, where are Russian researchers, programmers, and solution developers on the global scale? Do we as a society need to implement any additional programs and initiatives, if I can say so, to make our specialists in artificial intelligence more competitive on a global scale?
I can say that our top scientists, researchers are really compatible on the top worldwide level. You can see this, for example, on this NIST test. If you see on the developers, list of developers, you can see some other Russian companies there too. They are top ranked for last several years too, and we compete with them on not only in the NIST but also on our local market. So our solutions are quite good. And also, for example, you can see some other technologies in computer vision. For example, self-driving cars. That is a very difficult technology for computer vision, and you can see that some solutions, for example, Yandex self-driving car is one of the top performers on this side. So I think that our top scientists and researchers are on the real world level. And also you can see that you can, on some conferences like CVPR, ICCV or ECCV, when you go to some poster sessions or some orals, you can see that there are lots of Russian researchers that are working abroad and doing their research there.
Okay, thank you for your opinion.
Okay, so I will continue with this slide. in the end of my talk, I want to mention the Computer Vision and Deep Learning Summit, Machines Can See, that is organized by VisionLabs annually since 2017. Usually it is in the beginning of summer, in June. Last time in 2020, it was an online event that lasted for 3 days. Each year, we invite top speakers that are great computer vision scientists from top companies. I don't know which format will be next year, but we invite everybody interested in computer vision and deep learning to join us and have a good time with us. So this is end of my talk, and I'm ready to answer if there are some questions not answered. And thanks you for the attention. I hope it was useful for you, and it was interesting.
Yeah, so let's start with Q&A. There was a question from Anna, which I asked her to keep until the end. So how do you acquire extra new data, given the importance of privacy issues related to biometric data?
Okay, so talking about the privacy issues, we are operating in due to laws of the country. So if data is, we do not store any personal information about people. So we have no privacy issues on this side of storing some private biometric information. So biometric templates such as descriptors are not private, some private personal information that is confirmed with some additional tests and certificates like GDPR compatibility. So we do a lot of effort to not break the law of countries where we work, and we also protect our data and encrypt our data and protect from unauthorized access, so no one can steal data from our system. I think I tried to answer this question.
So the next question again from Anna. How do you detect video spoofing attacks? Using very good screens, e.g. 4K, with a normal camera, not IR, not infrared.
So if we don't have infrared, there are small textures that is quite hard for human to see, for example, but these textures, low-level textures, can be detected by neural networks when we train them on labeled datasets. So it is hard, but neural networks can solve this task only on the RGB images used as the input.
Okay. Next question from Mikhail. Any details about the architecture of your facial recognition network? How did you manage to make it so fast and keep accurate at the same time?
So the answer here is that we did try a big variety of different neural network architectures, and also did some neural architecture search and varying parameters of efficient neural network architectures. And also we focus on obtaining the highest accuracy by using distillation techniques that I mentioned in my talk before. So we use some neural architecture search, you can tell, and usage of knowledge distillation technique.
Okay, thank you. A question from Evgeny. What methods do you use to fight bias in data? Just collect more data and create less biased data sets, or use some kind of smart sampling bias aware loss function for training?
in some cases, you can reduce the amount of data that you have. For example, if you have classes with, for example, thousands of images in a profile, this much bigger than you need. So you can reduce your data too, or you can use smart sampling, as it is mentioned in question, to make your data also more balanced.
Thank you. Question from Elena on ethical aspects of face recognition. Continuing on the ethical aspect of face recognition, is it only a tiny step? It is only a tiny step to link your face recognition to the ID database, like you showed in the Emirates. Are we entering the state of total surveillance? And if yes, are there any ways to circumvent it?
Okay, it's so the ethical aspect of face recognition is quite hard question, but what I think is that usage of face recognition should be done with all the responsibility that some companies and vendors must have when they develop this algorithm. So I don't think that we entering a state of total surveillance, because if you think about it, we are already here. For example, it's much easier, for example, to find some, for example, criminal using some additional information such as telephone number or credit card paying, and so this is not a new technology for our days in terms of total surveillance, I think. So face recognition, this technology is, there are bad ways to use it and good ways to use it. So we focus on good ways, and the bad ways should be restricted by the laws of the countries, I think.
I think that Elena is interested of the ways how to avoid this if this happens. However, I agree with you that even having a knife at home is a dangerous thing, because knife you can use either to cut onions or to cut anybody else, right? So ethical aspects of AI is a very popular topic right now, and I think it's not the issue of our talk today. And we understand that every good technique or a product can be used for good or for bad. And there are many, how to say, applications of face recognition, which is really, really helpful. And we see that our life is improved with the use of these techniques. And of course, if this come to evil people, they will be able to use something evil. And just we have to control evil people, not the technology, right? Because the technology is just a thing which we use. Okay, so next question is: do you have papers published from on your name or on the name of VisionLabs?
Yes, we have papers, and the list of this, some of these papers will be in the useful links list that we will provide after the translation.
Yes, so there will be a post-event email, and we will share all the links. I will copy the links for the YouTube channel just in a couple of minutes. And again, you will have all these links in your emails. So a question from Evgeny. Have you tested your models on trillion pairs data set? And if yes, what results have you got?
We didn't test our models in trillion pairs data set in test splits, but we can say that we use training data from this, and this is No, we didn't test.
Okay. So it's been a great long time together. We are coming to the end of our meetup, and I would like to say a very big thank you to Dmitry for his talk. A very interesting story, its impressive presentation, and tons of useful information. Thank you all for your time, questions, and comments. As we have to wrap up now, just a kind reminder to fill in the post-event questionnaire. Please check your emails tomorrow and keep an eye on the updates from the Deep Learning AI. We have some new events coming soon at Moscow, Russia Pie&AI meetup, so stay tuned. Goodbye, and just wait for a second. Yes, the recording will be available in a couple of days. Again, you will get the link to the recording in the email, and I will just in case copy this link in the chat right now. Just give me a couple of seconds. I will find it and do it for you.
Thank you for the invitation, and I hope it was interesting and useful for you. And
Dmitry, it was amazing, and as I said, it's really great to hear from the person who is at the far front of the advances here. Thank you very much.
Thank you.
We are closing now. Bye-bye.
Bye.